Okay, so today we will start with the notion of rigid monoidal category. Categories. So, monoidal category C is called rigid if every object of C admits a left and a right dual object. And we will recall the definition of dual object just after this definition. So if every object of C admit a left and a right dual object. Dual object. So we will define the notion of left and right dual objects. So I wrote left and a right. This means that the left dual object should not be necessarily the same as a right dual object. You can have a left and a right dual object. Okay. So what is a left dual object? So an object X star in C is called a left dual, so left dual of X in C if there are two morphisms. So the existence of such a dual is conditioned on the existence of two morphisms. And this, if there are two morphisms, so evaluation morphism f x from x star tensor x to 1, and the second morphism called co-evaluation, which is in some sense dual notion. Yeah. I have a mistake in my note. One to x star. So co-evaluation map. So it's dual. You start from 1 and you go to x tensor x star. So there is a way to represent this morphism by picture So this morphism should satisfy some properties. We will write later, but just after that. But before writing that, let us write the pictorial representation of this morphism. Pictorial representation for this morphism. So you can represent it as like that. So you start from x star tensor x. So you draw like that, x star x, and then you go to 1. So it's a usual way to represent an element in the morphism, the home space. Yeah, from x tensor y to z. Here you have x star x1. Or in this case, you can just represent, because the morphism, the object 1 can be represented by just an empty edge, or you can represent it as follows. The usual pictorial representation is like that. So in that sense, you only keep the orientation of x here. You are doing like that, and the 1 is hidden. Okay, and similarly, you can represent the co-evaluation map like that. 1 x star x, or just by a single like that. And similarly, we keep the orientation of x. Okay, so this is a way to represent this morphism. So now this morphism should satisfy some properties to define a dual object, a left dual object. So such that, so these two morphisms such that the following composition are identity morphism. So we will write two compositions, and these two compositions should be identity morphism, and then we will write the pictorial representation of this composition called, and this equality with identity called, the zigzag relation. So everything is quite, so when you will write, I will write the composition, this may look complicated, but in fact, when you see the pictorial representation, everything becomes clear. So first, the composition. So you start from X. X is, so by convention, we know X is 1 tensor X. So you can apply the co-evaluation X on the 1 component and the identity on X. And then what you get is X tensor X star tensor X. This is okay. Then you apply the associativity constraint to move the parenthesis, X, X star, X. So you get X tensor X star tensor X. You apply the identity of the first component X, and then you apply the evaluation map. And what you get is X. Tensor 1. You get X tensor 1, which is X. So you get a map from X to X. And this map is assumed to be identity. And you have another map, should be identity. So it's the same ID. So I will be quick. So X star, which is X star tensor 1. Here you can apply ID X star tensor coev X. So you have X star tensor X tensor X star, and then you apply the associativity constraint. In fact, you need to apply the inverse because the parentheses are not in the good order. And then you have that X star tensor X star, and then you apply the evaluation map. Tensor identity X star. And then you come back to one tensor X star, which is X star. So this is identity. So identity and X star. These two compositions provide a map from X to X and from X star to X star, and by assumption, there should be identity. Okay. And there is now what is a zigzag relation, which is the pictorial representation of this equation. So picture pictorial representation called zigzag relation. And this is really intuitive, really easy. So you remember we will use this representation for evaluation and co-evaluation map. And then there is a very easy way to represent this composition to be identity. This is the following. So the first is as follows. You do like that. Start with X. You have X. Do like that. You have X here. This is the evaluation map, and you have a co-evaluation map here, and then X. This is the identity. First. And the second is the same. You start with X star, and you do like that. Up. You finish with X star, and you have evaluation and co-evaluation map. And this is identity of X star. So you see, so I will not explain in details, but you can decompose So you can decompose step by step, and you recover exactly this composition and this composition. So if you want to know the details of how to decompose this picture, you should go to last semester material, in fact, in the slide, because this is not in the book. This is some additional part from the book. In the book, they don't use pictorial representation. But it's good here to have an intuition of what is pictorial representation. Intuition due to pictorial representation. Anyway, so you can do the same. As I said, to be rigid, you need to be left and right, to have a right dual. So for the right dual, this is similar. I will not recall here. You should go to the last semester material. That idem for right dual. So everything is almost the same thing, but sometimes it's on the right instead of being on the left or something. For right dual, denoted, you have the star like that. And so the same, and we can take the following. The right dual of the left dual can be taken by X itself, and the left dual of the right dual can be taken as X itself, assuming they exist, assuming the left and right exist. Yeah, assuming star and star X to exist. Okay. So if it exists, you can just take like that. And by convention, also, the convention is to take, for the unit element, to take one itself for the left and right dual of the unit. Okay. So, yeah, that's okay. So you see how this picture is intuitive. In fact, this means that you have something, you can deform it continuously, you just into a straight line. So yeah, and there is no problem. In fact, this picture is exactly the representation of that. It is just that, nothing else. So it's it's easy. Once you know the pictorial representation, it's easy. You know what is the meaning of this. Okay, so now we will recall the notion of adjoint in locally small category, and we will give the link between adjoint and dual as we just defined. Left dual, right dual of an object, and the notion of adjoint of a functor. In fact, these two notions are related in the sense we will explain now. So, as before, as for the pictorial representation, this subsection was not in the book, but in fact, this subsection was more or less admit in the book, but it's good to recall this notion of adjoint of a functor, because we may need it. So, okay. So let C, D, B. Wait. C, D, B, 2 locally small locally small. I recall that which means that the morphism between two objects form a set. So this is out of the book. Out of the book. So you have two locally small categories, and you take two functors. Consider two functors f from D to C, G from C to D, such that so we will have a condition which look like the notion of adjoint matrix, where the Hom set plays the role of inner product. So you will see, such that for all x in C, for all y in D, there are natural isomorphism denoted alpha x beta y, such that not such that, but the following as follow. So you start from the functor, this functor, so you have the functor which from an element of D, so it's to wait, I want to make that shorter. So a functor like that. So from an element of D, the element of D will be here. Associate a set which will be the Hom set, this Hom set. And here you apply, so you have this functor. And you apply the natural isomorphism from this functor. So this is the arrow for natural isomorphism to this functor, Hom D, here, G of x, from D to set. And similarly, this is a functor from D to set. So you put the element of D here. So you have this functor like that. So one natural isomorphism like that, and same for beta for with the category C. So Hom C f of y, and you have that from C to set. So this corresponds to element here. and you apply. You have the natural isomorphism beta y C y J C to set. So you have this natural isomorphism. So you see, it's like it's like you are moving this here, or you are moving this here, exactly as when you define the notion of adjoint of a matrix. And the offset here plays the role of inner product. Okay. So the notation C F Y X with an isomorphism natural isomorphism D Y G X natural isomorphism. And as I said, it's like the notion of adjoint of a matrix. So you have something like that. So you move. Okay. So analogous to the notion of matrix adjoint. Where functor correspond to matrix and set correspond to inner product. Okay. So under this condition, the functor F is called the left adjoint of G, and G the right adjoint of F. As for a matrix, the adjoint matrix. So F is called a left adjoint of G. G is called a right adjoint of F. So this is a definition for left and right adjoint. Yeah. So then under this assumption, you have F is a left adjoint of G. Is a definition from being a left adjoint and a right adjoint. Okay. So now, what is the relation with the notion of left dual of an object we already we defined before? We will need to consider the monoidal category of endofunctor of the category C. So proposition, if so you take C equal D, locally small category as above, and consider the monoidal category of functor from C to itself called NC Then the above f and g, above f is a left adjoint of G as functor in C, if and only if, as a functor in C, if and only if F is a left dual of G as object in ANSI. So you see, as object in ANSI. So you have two levels. You have the level of the category C and the level of the monoidal category on C. And the notion of adjoint functor in C corresponds to the notion of left dual in on C. But on C is a specific example of monoidal category, even if it is universal. But if it is a specific one, so we can completely cover the notion of left adjoint from the notion of left dual. So in that sense, the notion of left adjoint is the notion of left dual generalize the notion of left adjoint, because it can be covered on a specific monoidal category. And we can define the same for the right dual and right adjoint. Right adjoint, right dual. So yeah. So as I said, remark, the notion of left dual cover the notion of left adjoint. Just need to consider the specific monoidal category on C. Yeah. So I want to put that just after that, like that. So same for then for the right adjoint and dual, then you can include that includes the remark also. So the notion of left dual covers the notion of left adjoint. So in that sense, the notion, no, I will write like that. In other words, the notion of left dual generalize generalize the notion of left adjoint. Okay. Okay. What time is it? So that's good. Like the notion of left adjoint in category theory is a very deep tool. So it's good to have for this deep tool to be covered by a notion for monoidal category we are working with. Okay, so this was the end of the part out of the book. End of out of the book part. We start from here. Out of the book. Okay. So now we are more familiar with the notion of adjoint, and we will use that. So okay. So proposition. Proposition. Let's see. So what is the proposition is about? This proposition. This proposition says that if a left dual exists, if the left dual of an object exists, then it is unique, up to unique isomorphism, preserving the evaluation and co-evaluation map. So this is a proposition about the uniqueness of the left dual when it exists. So let C be a monoidal category. If X in C has a left dual, then it is unique up to a unique isomorphism preserving the evaluation and co-evaluation morphism. And same for the right. Same for the right. And So this. Okay. So I got a small trouble with my laptop. It should be okay. So and off. Okay. So this proposition is in the book. In fact, this proposition is quite long to prove. Last semester, this requires 7 slides to prove that. So, as I said, for this summary part, we don't do the proof. So we will skip 7 slides of proof of this proposition. So this proposition is quite important. Proof. Si last semester's material. Material. It required 7 slides. And in fact, we did that. At the end of session 11 and at the beginning of session 12. We finished the proof at the beginning of session 12. Last semester, session 12. Last semester, session 12 started with the end of the proof of previous proposition. Okay. So now we can make the pause. We can make the pause. Okay. So now we will define the notion of dual for morphism. Dual of morphism. Dual of morphism. We will recall. So if x, I in C have left dual, x star, y star, so from then from a morphism x from x to y, we define its dual, left dual, denoted f star, from y star to x star, as follows. So you will have, so it will be defined as a composition And as for the zigzag relation, in fact, we will have, so don't worry, we will have a pictorial representation of this composition, which make everything intuitively clear. So you have f from x to y, and we want to define something from y star to x star. So you start from y star, and you apply. So you know that y star is y star tensor 1. You apply like that identity of y star tensor co-evaluation of x applied on the 1. So you have y star, and then you have x tensor x star given by the co-evaluation. Here you apply the usual associativity constraint in fact to inverse. So y star x x star, you move the parenthesis, y star tensor x star, and then you apply so on the first component, you apply identity y star tensor f, and for the identity x star for the second component, so of the tensor product. So you have something like that. Tensor. So identity go to identity, f x go to, and this is the identity. So it's okay. And then so you apply the evaluation map of y and the tensor, the identity of x star. And what you get is one tensor x star, which is x star by convention. So we have a map from y star to x star, and this composition is f star. As the following composition. As the following composition. Okay. So this composition is the definition of f star. So what is the pictorial representation here? So picture, which makes everything intuitively clear. So first, the morphism f is represented like that, just a box. And f star, this is exactly like that. You start from f, and then you do like that. Tac, tac. Ah. That. Okay. No. That should be below. So, like that. Okay. So here you start from y star. You finish with x star, and all the intermediate can be understood as the previous composition. This is an element in this Hom set. And here you have the evaluation and co-evaluation map. This is identity, etc. So, and here you don't see, but you apply some maybe some associativity constraint if you need. Okay, so this is a picture for the dual. So you see, this is like if you rotate, in fact, you make a rotation of the morphism. Anyway, so you have the same for the right, same for the right dual. Okay. The dual of a morphism, left dual. Now, what is the next proposition? Okay. So the next proposition will be will state that the monoidal functor preserves the left dual. Proposition. Monoidal functor preserve left dual. And same for right dual, of course. So how to state that? So let CD be monoidal category let F. So a monoidal functor, so you recall that a monoidal functor is given by two objects, a functor F and a monoidal structure, and we prove that we get an isomorphism phi. We can prove the existence and make it. So we have the data of two, the first two, and the third can be make. So you have this to be monoidal. So in this notation, the phi is redundant, but we will need it. So I write it like that in the former way. So be a monoidal functor. So you have the functor from C to D. So you take an object in C, admitting a left dual. Then we can take like that. We can take f of x star as the left dual of f of x. In other words, we can take f of x star equal f of x star inside the parentheses. We can take this one as a left dual of this one. This is the meaning of that. And why? So I will skip the proof as usual for the summary part. Proof, int proof. So what's that? Proof? Proof int. Int define define the evaluation and the co-evaluation map for f of x using f, g, and phi. So in fact, there is a quite natural way to define this map, this morphism, using f, g, and phi. So I skip that. You can see the details in the last semester material again. Okay, so proposition. So now this proposition will be about how the dual of morphism of objects deal with the composition and tensor product. Object. Yeah. So dual of object or morphism composition and tensor product. Tensor product. So take U, V, W in C monoidal category. C is a monoidal category. Assume that U, V, and W have left dual. So U star, V star, W star. Then the following equality hold. So first, how the composition of morphism deal with the dual. So you just switch like that. And how the tensor product of objects deal with the dual, you switch also. So wait, I hope I did not make a mistake here. Let me check. Where is it? Yeah, it's okay. No mistake. So you switch. So I don't remember. There is another. There is another operation where there is no switch, but this is not here. I always forget which one. But anyway, here it's okay. So there is no switch. So here there is you switch. Okay. But in fact, this is easy to see why you should switch, because yeah, in fact, it's easy to see once you have the representation, the pictorial representation. Picture. You have G, F, and you do the dual like that. So as I said, the dual is like making a rotation. So what you get is you have F here like that, and G here like that. And wait. So in the middle you have zigzag relation, and this is F star G star. F star G star. This one's too small. Okay. This is a picture for the first. And for the second one, let me remember. I guess I already drew something. Anyway. So for the other one, if you do, for example, you have U, V, W. And if you apply something like that, you have here it's V star, and here it's U star. So in this W star. So if you start this is from U tensor to W, you apply the dual, and you have a morphism from W star, V star, tensor U star. And so you see that this switch, so this is okay. Okay. So I spent too much time on that. It's not good. So proposition. So the next proposition is about natural adjoint Chang isomorphism. So the next proposition will use the addition part about adjoint functor. Natural adjunction isomorphism. So okay, so so you take an object in a monoidal category, monoidal category C, and you assume that this object has a left dual. left dual F star, V star. Then the functor by tensoring by V star on the left is a left adjoint of the functor by tensoring by V on the left. So let me check. This is suspicious. This is suspicious. I would prefer 12. Left adjoint. Okay. It's okay. In other words, there are natural adjunction isomorphism as follows. So C U tensor V to W, and then you recover why I draw such a picture here. So natural isomorphism with this set U W V star, and between V star tensor U W with like that, V tensor W. So you are moving here, and this one are moving here. So the same as before for the analogous of adjoint of matrix, and offset correspond to inner product. So natural adjunction isomorphism. This is natural adjunction isomorphism, the sense of what we define here. Natural isomorphism. This one. This is in that sense the sense of natural adjunction isomorphism. Okay, and you have the same for right dual. Okay, so that was the end of the summary of session 12. So now we can start to summarize the session 13. And we start the session 13 by providing a picture for the natural adjunction isomorphism. So alpha beta. So alpha here. Alpha beta. Alpha with some index, maybe. I don't remember. So picture. So you have U, V, W, And you do like that. UV. You are doing like that. So this is alpha. This is the first. You have alpha. Let me write like that. Alpha, beta. And for the other one, wait, I need more space. Then for beta, you do like that. U, W. V star. So what is the point? So is it like that? No, not here. So you start. So wait. Okay, and then you do like that. So this is beta. So like that, there is alpha, there is beta. Okay. And this is beta. And so you see, you can compose. When you compose the two alpha beta, U, V, then you just need to apply the so this is that U, V, W. Zigzag relation. Equal by zigzag relation by zigzag relation. So the zigzag relation applied here. Okay. So which mean this means that beta composed with alpha is identity. Yeah. So okay. You see the picture for the natural adjunction isomorphism. So you have also picture for, we draw picture for that, but we can have picture for that. Same thing. Okay, so now so what about now? Now we can define so at the beginning of the section we define the notion of rigid monoidal category, and we define it as having object with left and right dual. And then we recall some result about left and right dual of object and morphism and some picture. And now let's come back to rigid monoidal category. So, and a rigid monoidal category is a category where all the objects are rigid. And an object in a monoidal category is rigid if it has a left and a right dual. It's called rigid. if it has left and right duals. Duals, the plural, should not be, may not be the same. Monoidal category is called rigid if all its objects are rigid. Okay, so now we know what is a rigid monoidal category. So what about example of rigid monoidal category? So the first example, more or less a trivial example, which is a category of finite dimensional vector space, monoidal category vec of finite dimensional vector space. And the finite dimensionality assumption is very important. Finite dimensional vector space K vector space. So finite dimensional monoidal category vec of finite dimensional K vector spaces is rigid. And I insist, it's not true if it is not finite dimension. So, what about the tool? So you can take V star for a vector space. You can take the left and right dual equal here as the dual space linear form of a vector space V. And the evaluation map will be just the application of the linear form, so the contraction. You have a linear form, you have a vector, you just apply the linear form on the vector. So it's called a contraction. And the co-evaluation map, here you start from the field and you want to go to V tensor V star. So you just need to define the image of 1, because everything the field is one-dimensional. So you define like that, V tensor V I star. So you ask the image of 1 will be this sum where Vi, the basis of the vector space V, and Vi star, its dual basis. In V star. This is very usual notion in linear algebra. And recall that this sum is independent of the choice of the basis. And as I said, so I should put that in red here. The there is no co-evaluation map. Co-EV in the infinite dimensional case in general. So in general, you cannot define co-evaluation map. More or less, because here you have a sum, and then the sum would be infinite, so you should have maybe some topological problem. Okay. So, second example of rigid monoidal category. And there will be a third example, but I'm afraid we will not have time for the third example today. So example 2. The monoidal category Webpage of finite dimensional representation of a group J over a field K is rigid to so you just need take V star, the evaluation and co-evaluation map as for VEC. But where? So the representation for V star, what is the representation? You need to, because it's a category of representation. So you need to define the representation for V star, even if you can define V star as a vector space. What is it represents what as a representation? So the representation of V star applied on an element of the group. So this means representation. This means dual object of V, and this is an element of the group. So how do you do that? You use the representation of V applied on G, but then you take the inverse of this matrix and the adjoint matrix adjoint. So I have a doubt here. Maybe like that is better. I guess it is the same because it's a representation. So but it's better like that. So inverse group inverse, and here the matrix adjoint. But because it's a representation of group, you can also put that here, and this will be the matrix inverse. But it's more elegant like that. So that's all for today. So example 3 will be next week, next session. There's no time. 2 minutes. Yeah. Next session. So this will be anyway. So let's stop here. We'll stop here.